All right. Welcome to part 2 of the Lepton Triptych for the first paper of the triptych. In this one, it'll be relatively short, mainly so that I can actually upload it to YouTube in less than a 24-hour time span because they've changed the way things upload and it's kind of tedious. And another reason is because this next section is kind of long, so I'm breaking it up into parts. But first, before we begin, I'm going to cover an error that I made in the last video that I what do you call it? It was namely in computing this value here. I was seeing that it did what do you call it? That they anti-commuted. But there's an important thing is that it turns out that if you actually carry out this computation, it's equal to 0. So even if it anti-commutes, it's equal to 0. So that means that what do you call it? That implies that row naught and row 1 they have a commutator of 0. So just to prove real quick, we know that this is equal to 1/4 times E1 bar plus E2 bar, and then times E2 plus E1 bar, E2 bar. And we can see that it's 1/4. Get E1 bar, E1, E2, and then plus E2 bar, E1 bar, E2 bar, then plus E2 bar, E1, E2 plus E1 bar, E1 bar, E2 bar. And this term right here will cancel with, let's see, it'll cancel with this term. Wait, hang on. What term am I thinking about? E1 bar. Oh yeah, it'll cancel with this term, and these two terms will cancel. Okay, so that's the errata. So now let's move on to what we're actually going to talk about. Let's first recall some properties of the algebra developed in the last video. Just two properties, namely row naught squared is equal to minus, and then it's this idempotent here. And also the box is equal to 1 minus this right here. This paper uses these two properties to generate a spinor space required for lepton fields. So let's discuss what the space will be. The spinor space for leptons or lepton fields is a minimal left ideal. Highlight that or underline that, but MLI is usually how I will shorten it. So what is an ideal? Let's first define ideal. It is a subset S of an algebra A, such that for all elements of the algebra and for all elements of the ideal, or for all elements of the algebra, And for all elements of the ideal, A times S is also in the ideal. So it's just saying that, what do you call it? It's just saying that if I have an element of the subset S and then I multiply it on the left, if I multiply it on the left with A, then it stays in the subset S. And that's called an ideal. And it's called a minimal left ideal specifically because A is multiplying on the left here. And it's minimal because there's no smaller ideal, like there's no subset of S. There's no like curly S that's a subset of S, which is a subset of A. This doesn't exist. So that's why it's minimal. Now let's talk about the geometric algebra we're in. Again, the geometric algebra G4 in which this paper takes place has 2 to the 4th, so 16 basis elements. Basis elements. And those are 1, E1, E2, E1 times E2, E1 bar, E2 bar, E1 bar times E2 bar, and then B1, which is equal to E1, E1 bar, B2, which is equal to E2, E2 bar, and then B1 times B2, E1 bar, E2, E1, E2 bar, E1 bar, B2, B2, E1, B2, E2, B1, E2 bar, B1. These are all the elements of the algebra. But multiplication, if we multiply elements of this algebra by the box, then we make pairs of elements indistinguishable. So certain pairs of these will be indistinguishable, and we'll see which ones. But another way to say this is that multiplication, or another way to say this is that the box generates a minimal left ideal. And we call this minimal left ideal S. Let's put this on there. G box such that G is an element of G4. So this G here is a multivector. And this is the element of the ideal such that any object in the algebra times it is still going to be in the ideal. And so box is something that generates this. Let's see what the basis is for this. Its basis is the following. First, we have box. That's kind of like the identity, but it's also, you can see that you can prove that it's equal to these. So these are equal. And then E1 box, E2 box, and then E1, E2 box. These are all equal to different things. So this is minus E1 bar, B2 box, minus B1, E2 bar box, minus E1 bar, E2 bar box. And then we have B1 box, E1 bar box, E2 bar box, and E1 bar E2 box. This is just equal to B2 box, E1 B2 box, E2 B1 box, and then E1 E2 bar box. Then we're gonna just choose 8 of these because there are 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And because they're equal, it reduces the dimensionality of the space from 16 to 8. And we're just going to choose this as one of the bases, this one of the bases, this is one of the bases, this is one of the bases, this, this one, and this one. I'm going to choose these as bases. So reduces it from 16 elements to 8 elements. And for ease, we can choose these 8 elements here to be multiples of E1, E2, and E1 bar. The reason for this is because if you have a basis element with, or if you have a geometric algebra with 8 basis elements, then it functions effectively like the 3-dimensional algebra. So we have effectively reduced the dimension. And so I'm going to choose to represent things in E1, E2, and E1 bar because it's like having your X, Y, and Z directions. So let's rewrite this all. So I have box, then E1 box, E2 box, and then E1 bar box, then E1, E2 box, and then E1, E1 bar box. And this is the same thing as having B1 box, by the way. And then E1 bar, E2 box. And then we have lastly E1, E1 box, or bar, E2 box, which is just the same thing as E2, B1 box here. And these all have equivalencies. So let me copy and paste these. Okay, so these are all equivalent to things in in the geometric algebra the 3D space. So here we just have, this is S, and then we're going to have objects in G3. Yeah. So this red is technically not tangent. There we go. Okay, and this will be equivalent to the 1. This will be equivalent to your sigma X direction, sigma Y, sigma Z. And then here, it's sigma XY, sigma X, or sigma XZ, and this is sigma ZY, and then minus sigma XYZ, which is equal to just minus the pseudoscalar. So you can see the correspondence between the minimal left ideal, which becomes isomorphic to the, what do you call it, the algebra of physical space. And so we can take this spinor space reduces. Okay. That was interesting that it wasn't working. Reduces to reduces to, reduces, there we go, to S. It's still G times box, but now we can say that G is in the algebra of physical space. We can say that it's an element generated by the E1, E2, and E1 bar, because we're ignoring essentially an entire degree of freedom, or 8 degrees of freedom, when we go to the spinor space. But then we can extract complex structure from this space. So what this space does to extract complex structure actually is the following. The paper extracts, and by factors out sigma x z, such that you can rewrite G3 as an element from the geometric algebra 2-dimensional space added to another element of the geometric algebra from 2-dimensional space times sigma xz. And just to reinforce the idea here, this sigma xz is equivalent to B1 in the, what do you call it? In G4, which, because even though we're saying it's G3, we're not actually in G3 here. It's just isomorphic to it. But we can use the fact that it's isomorphic to factor everything. And so this means that we're going to factor the spinor space. So S can be further factored and reduced into the form A box plus B box, and then B1, such that A and B are in G2. All right. And so this has 4 degrees of freedom. This has 4 degrees of freedom. That's the total 8 degrees of freedom that are in here. And let's just prove this real quick, because and to do this, I'm just going to work within the algebra of physical space because it's completely the same. Just replace elements of this in the APS with elements here times a box. So you can imagine it like this. If I have A in G2, or A and B, then I have A equals some A naught plus A1 sigma x plus let's see. Trying to remember. Oh, this is great. I accidentally erased my whiteboard. Not accidentally, but I just forgot. And then I erased my whiteboard, which had this calculation on it, so that I could copy it. Well, it's a little unfortunate here, but I have A2 sigma y plus A3 sigma xy, and then B, it has the exact same form, which is B naught plus B1 sigma x plus B2 sigma y plus B3 sigma xy, like such. Okay, no, I think this is correct. I'm doing this all correctly. And so you can see that if I take A and then plus B, okay, well, I thought that I had just muted, call it phone break. Thought I just muted all of my notifications. It's great. Sigma XZ here. And then if I I pull this, I expand everything, I'm going to end up with all of this. Then plus B naught sigma XZ plus B1 sigma Z plus B2 sigma XYZ plus B3 sigma, or then it'll be minus and sigma YZ. Like this. And you can see that I have every basis element for G3. I have a scalar, all of my vectors right here. And then my bivector, my bivectors right here, and then a pseudoscalar. And so I can factor an element of three-dimensional space into the to the sum of two-dimensional space objects times this bivector. And it's the same principle that has just been used here to factor the minimal left ideal that the lepton fields will live in.